This is Pierre-André Mathieu, and today I'm here with a tutorial on setting up a camera a different way, modular style. Now, I'm going to play my project. As you can see here, I have a fully functional camera where I can move horizontal and vertical. Once I click the right thumbstick, it smoothly resets the camera like this. A lot of people on my previous tutorial, in the comments say that they're having difficulties with this, and I can understand that. In this video, I'll do my best to explain as I can on how I set up the camera system this way in a very modular sense. Okay, what I have here is called the player camera. I'm gonna tell you why I use the player camera blueprint actor instead of, putting a camera system within the player character itself. What I did here is a fairly advanced architectural choice. I've decoupled my camera from my player character. In standard Unreal Engine third-person template, the camera boom and follow camera are components physically attached inside the character blueprint. By using those two components within this actor blueprint, I've given myself complete independent control over how the camera behaves. In the components panel, as you see here, I have a standard setup, a camera boom with a follow camera attached to it. But because the player camera blueprint is in itself a standalone actor, it doesn't automatically inherit the rotation or jitter of the character's physical capsule. It's crucial for action games where the character might be flipping, rolling, or snapping to targets. But I need the camera to remain smooth and stable. I have several flow variables to mathematically drive the camera's behavior rather than relying strictly on the default spring arm settings. This is unlock interp speed, and the exact value for it is 3.0. This strongly ties into the lock-on system, in which I will be covering on tutorial number 9. It suggests I have logic to smoothly interpolate the camera back to a default state when I disengage from an enemy rather than snapping wildly. This is the default arm length. Its default value is 540. I'm storing my standard camera distance as a variable. This allows me to easily reference it, and likely means I plan to dynamically change the arm length during gameplay, such as pulling the camera back for a large area of effect attacks, or pushing it in tight for enclosed spaces. Those two extra are angle exponent and camera rotation rate. They suggest I'm applying a custom math to how the player manually rotates the camera, likely implementing a custom easy or acceleration curve so the thumbstick camera movement feels heavier or more cinematic. The center camera input function I'll explain on a much later segment, but what you need to know is that this specific function here confirms I'm building a dedicated action game camera mechanics, allowing the player to click the right thumbstick to instantly snap or smoothly pan the camera directly behind the character's back. So by putting all this in player camera blueprint, my character blueprint only has to worry about health, stats, and stylish combat logic, while this blueprint handles all the framing and cinematography. Now, let's get to the core engine of my decoupled camera system. I created this to create a cinematic elastic camera that feels smooth and responsive, which is essential for fast-paced character action games. Rather than having a camera rigidly bolted to the player's back, this setup allows the camera to gracefully chase the character hierarchy here. By immediately capturing the delta seconds from the event tick and setting it as a variable, I ensure that all subsequent camera movements happen at the exact same speed regardless of whether the player's PC is running at 30 frames per second or 120 frames per second. I use a sequence to strictly enforce the order of operations. The camera must calculate its new position and rotation before it calculates its zoom distance and camera auto adjustment. Now, on to the part where I smooth the chasing and gimbal lock prevention. This here is the elastic follow. What I'm doing here is This is the elastic follow. What I'm doing is I'm grabbing the player character's location and using it as the target for the camera. By interpolating the vector rather than just setting the location, the camera briefly lags behind the player during sudden movements such as a quick dash before catching up, giving the movement a heavy dynamic feel. For the rotation, I use the anti-nausea pinch clamping, which is the one right here called a clamp float. What I'm doing here is I break the camera's current position and run the pitch through a clamp set in between -60 and +60. The purpose here is to prevent the player from looking entirely straight up or straight down, which stops the camera from flipping over itself, a mathematical problem known as gimbal lock, and keeps the horizon grounded. I multiply my unlock interp speed by 1.5 before feeding it to the R-interp2 node. I designed the camera's rotation to snap into the place 50% faster than its physical location tracking, ensuring the player never loses sight of what they are trying to look at. This right here is the rubber band effect. I'm constantly calculating the distance between the current target arm length and my variable default arm length. If the camera gets pushed close to the player, for example, if I back into a wall and engine collision pulls the spring arm in, it won't just abruptly snap back to 540 units the moment I step away from the wall. Instead, it smoothly glides back to its default distance. By running all of this every single frame, I've built a self-correcting camera that manages its own framing. I built a self-correcting camera that manages its own framing, distance, and limits without needing the player to constantly babysit the right thumbstick. This function right here is the camera access input. It's very clean and modular input handling. By rotating everything through a single function with an enumeration, I basically avoided the whole spaghetti thing that usually comes with a camera logic. So I'm gonna have to break this down. This is a traffic controller. I'm using a switch on right thumbstick access node. It acts as a central hub. Instead of having a separate function for looking up and down and looking left and right, I use one entry point, which is highly efficient for debugging because I can see exactly which access is being triggered at any given time. This is the pitch logic, the local space. It's for the y-axis. I use add actor rotation. The pitch must be handled in local space. If I use world space here, the camera would tilt on the world's horizon, which feels wrong to a player once they start rotating the camera horizontally. I use the select node as a safety filter by tying the access value to the right thumbstick access pin. I ensure that the vertical input only affects the pitch input of my make rotator. This one right here is the yaw logic, the world space. For the x-axis, I switch to add actor world rotation. This is a subtle but correct distinction. Horizontal rotation usually feels much smoother and more consistent in an action game when handled in world space. It prevents camera roll or tilting of the horizon when I'm looking up at a high angle while trying to spin the camera. It keeps the ground feeling level regardless of where the camera is pointing. Here, the input is correctly routed to the yaw pin of the make rotator. Simply put, I created a mathematical isolation chamber for each axis. By using local rotation for pitch and world rotation for yaw, I prevented the camera from getting crook during intense, stylish action combat. This function right here is the center camera input. It's a sophisticated camera reset feature. It doesn't just snap the view, it mathematically realigns with my independent camera actor to the character's physical orientation, ensuring the player can instantly regain a proper perspective during fast-paced action. Let's break down the logic behind the implementation. The function starts by replacing, not replace, but what I'm saying here is that the function starts by reaching into my camera boom component and unchecking enable camera rotation lag. Well, actually I add a pin to a node here, but when I see it extract actually it'd be a lot easier if I were to show you. It's just as I said before. It all starts by unchecking the enable camera rotation lag, but I named the input to press instead of enable camera rotation lag because it happens whenever I click the right thumbstick to center the camera. Well, will happen, but you get the point. Anyway, I built my camera with elastic lag for smooth movement. By turning it off here, I ensure the reset is instantaneous and crisp, preventing the camera from swinging or overshadowing. No, I meant to say overshooting whenever I'm trying to center it. This right here is mesh-based orientation. I use getPlayerCharacter and specifically target the mesh component to get world rotation. It's a professional choice because by referencing the mesh's rotation rather than the capsules, I have to make sure the camera centers based on the direction the character is visually facing, which is more intuitive for the player. This is where the 90-degree correction logic comes to play. I break the rotation and add 90 degrees to the yaw before making a new rotator. In many Unreal character setups, the mesh is rotated 90 degrees to face the forward x-axis. I've accounted for this offset mathematically so that centering actually puts the camera directly behind the character's back instead of looking at their shoulder. After resetting the global rotation, I use Add Actor Local Rotation to apply a -15 adjustment to the pitch. What this does, it provides a high angle reset. Instead of the camera being perfectly level with the character's feet, it tilts slightly downward. This gives the player a better view of the ground and the surrounding combat area immediately after centering. So in short, I created a reset that removes lag for speed, aligns with the character's visual direction, fixes coordinate offsets, and provides a tactical downward tilted view. Oh, by the way, if you want the camera to actually lag, you're gonna have to place the check mark to true instead of false. In this segment, I'm going to talk about the creation I built here, the right thumbstick axis. It's a structural backbone for the modular camera system in which I've explained within my previous segments. By defining this enumeration, I've moved away from hard-coded spaghetti logic and toward a scalable professional architecture. I'm gonna open this and explain the structural design. What I have here are two distinct enumerators within this asset I've established. The right thumbstick y-axis, specifically designated for vertical input. The x-axis, same but for horizontal input. This enumeration serves as the language that allows my different blueprint functions to communicate clearly. Its presence allows me to achieve three major technical goals: switch-based routing, data integrity, and blueprint readability. As I've explained in the camera access input within the player camera blueprint, this enumeration allows me to use a switch node. This is significantly more efficient than using multiple branch if-then nodes, as the engine can immediately jump to the correct execution path based on the enumeration value. By using an enumeration, I eliminate the risk of magic numbers or string typos. When I pass an input through the system, it is strictly typed to either the X or Y axis, ensuring that vertical input never accidentally triggers horizontal movement logic. Instead of looking at abstract wires, anyone reviewing my code can instantly see that a specific logic path is intended for the right thumbstick y-axis. As you can see here, I created a new blueprint interface called the Player Camera Manager BPI. It's a clean, decoupled interface that allows my player character and camera manager to communicate without being hardwired to one another, which is great for maintaining a modular code base. I'm going to break this down into 4 specific functions I've built. This one right here is set player camera. It includes a camera input pin and a return value output pin. It lightly serves to pass a reference of the specific camera actor to the manager or character. The camera input function handles live data with 2 input pins, the axis value and the right thumbstick access type. This allows the interface to pass raw stick data directly to the camera logic. This function right here is a simple getter function that includes a return value output pin, allowing other blueprints to safely request a reference to the active player camera. And lastly, the center camera input is a dedicated trigger function with a press boolean input pin. This is designed to initiate the camera reset centering logic, in which I've discussed earlier within the previous segment involving the center camera input within the player camera blueprint actor. So by using this interface, I've ensured that if I ever decide to swap out my camera system for a completely different style, I won't have to rewrite my character's blueprint input logic. I'll just need to implement this blueprint interface in the new camera. Alright. This new actor here is the player camera manager blueprint. It's basically the child of the player camera manager. If you're confused, well, if you want to get the camera manager out, I right click, click blueprint class, then within that class I search for player camera manager and click on it. Then I can just rename it player camera manager, like the one I have here. I'm gonna open it. Inside here, I go to implemented interfaces, which is the one I have here. Then I search for player camera manager, which is the one I have here, and add it. By implementing the player camera manager BPI into the player camera manager blueprint, I created a standardized communication bridge that allows my character or controller to send commands to the camera system without needing to know the specific technical details of how the camera is built. The core purposes of this design are decoupled communication, event implementation, modular architecture and centralized control. My player character can now call functions like camera input or center camera input on the manager through the interface, ensuring that the character blueprint doesn't need a direct hard reference to the specific camera manager class. In the event graph, I've implemented the interface's functions as events. This allows the manager to listen for and execute the camera logic whenever those interfaces messages are sent. Because the interface is implemented under the interfaces section of the class settings, I can easily swap this camera manager for a different one later, as long as the new manager also implements the BPI. My input systems will continue to work without modification. By routing inputs through this interface into the manager, I've designated this blueprint as the brain for the camera-specific features like camera zoom and orientation resets, keeping my main character blueprint clean and focus on movement and combat. In the blueprint update camera function of my player camera manager BP, I've implemented a logic flow that dynamically spawns and update my camera base on the player character. I use the getCharacter interface call to retrieve the current character from the camera target. Then I perform a class isChildOf to check, verifying if the return object is indeed a character blueprint before proceeding. If the character check is successful, the manager calls spawn actor player camera blueprint. The camera is spawned at the exact transform of the target, using getActorTransform as the spawn transformation. The target here is the character blueprint object reference, by the way. The collision handling override is set to always spawn ignore collisions to ensure the camera isn't blocked during initialization. The resulting actor is saved to a camera variable. Once I have that, I immediately apply a data rotation of -5 on the y-axis using add actor local rotation, which likely sets a specific initial tilt for my view. The function pulls the world location and world rotation from the camera boom component. It also pulls the field of view directly from the follow camera component. These values are fed into the return node through new camera location, new camera rotation, and new camera field of view, with the return value booming check to confirm the override is active. This camera input here serves as the primary receiver for stick movement data coming from the player controller. By using the Player Camera Manager BPI, I created a reliable pipeline to pass this data directly to the camera actor itself. The logic here begins with the event camera input, which is a message sent through the Player Camera Manager Blueprint interface. Now, before attempting to move the camera, the system uses a validated get on the camera variable, a Player Camera Object Blueprint object reference. This prevents the game from crashing if the camera hasn't been spawned yet. If the camera is valid, the execution flow triggers the camera access input function on the target Player Camera Blueprint. The access value is passed directly from the interface event to the camera function to determine the magnitude of the rotation. The right thumbstick access type is also passed through, ensuring the camera knows whether the input is intended for horizontal or vertical rotation. This setup here is efficient because the Player Camera Manager acts as a traffic controller, validating that the camera exists before allowing any input data to reach it. The center camera input logic follows the same clean decouple pattern as my other camera inputs, serving as a specialized trigger to reset or snap the camera's orientation. The process starts with the event center camera input right here, which is received through the Player Camera Manager Blueprint. The event includes a press boolean input, allowing the manager to distinguish between the initial button press and release. To ensure the action is safe to perform, the execution passes through a validated get for the camera variable. This confirms that a player camera blueprint exists before sending further instructions. Once validated, the logic triggers the center camera input function specifically on player camera blueprint target. The press state from the initial event is passed directly into the final function, ensuring the camera actor knows exactly when to initiate the centering behavior. It's a great setup because it keeps the specific math or snap logic inside the camera blueprint while using the manager as a gatekeeper to ensure everything is properly initialized. Now, let's talk about the player controller blueprint. I've set the player camera manager class to my custom player camera manager blueprint to basically ensure the engine uses my specialized camera logic instead of the typical run-on-the-mill Unreal Engine system. Yeah, this one right here. Allow me to explain why this setting is critical for the project. By assigning this class in the details panel, the player controller will automatically spawn and utilize the player camera manager blueprint upon the possession of a pawn. This allows the manager to execute the custom blueprint update camera logic I've built, which handles the dynamic spawning of the player camera blueprint and initial rotation offsets. Since my controller sends input data through the player camera manager blueprint, this setting ensures there is an active listener to receive and validate those camera input and center camera input messages. It established my custom manager as the middleman between the controller's raw input and the camera's actor physical movement, maintaining the modularity of my system. This part here is where I've constructed a frame rate independent input pipeline within the event tick to drive my camera movement through the player camera manager blueprint interface. I'm going to break down the logic for then one of my sequence. Before the sequence, I capture and store delta seconds to ensure consistent movement regardless of the frame rate. The logic here multiplies delta seconds by custom time dilation to create a unified time scaler that accounts for any slow motion or speed up effects within my game. This is where the horizontal look logic comes into play. What I did here is calculate the horizontal rotation by multiplying the right thumbstick x-axis raw input by the base turn rate and my calculated time scaler. This value is sent through the camera input interface message to the player camera manager. The right thumbstick axis type is explicitly set to the right thumbstick x-axis to tell the manager which direction to rotate. This part right here is where the vertical look logic comes to play. Following the horizontal calculation, the execution flow triggers a second camera input message. The vertical rotation value is derived by multiplying the right thumbstick y-axis input by the base look up rate and the time scaler. The right thumbstick axis type for this call is set to the right thumbstick y-axis. Both interface calls use the getPlayerCameraManager node as the target, ensuring these messages are received by your custom Player Camera Manager blueprint. This setup ensures that my camera rotation feels smooth and consistent across different hardware and time dilation states. The Legacy Input Manager acts as the global bridge between physical hardware and my code. It allows me to define abstract action or access names which the player controller blueprint then listens for to drive its internal logic. I'm going to break down how my specific configuration ties together. This right here is the lookup rate. It uses mouse Y and gamepad right thumbstick Y axis. What I did here is I define an axis mapping. This access mapping that listens to both the gamepad right thumbstick axis and mouse Y. Likewise with turn rate mapping, the turn rate axis mapping listens to the gamepad right thumbstick X axis. By mistake, I have it mouse Y instead of mouse X. But it's not that much of a big deal because I can change it to mouse X. So yeah, turn rate, light look up rate is defined and by the axis mapping that listens to gamepad right thumbstick X axis and mouse X. Now that I've explained in this part, I'm going to explain how this relates to the inputs I have here in the player controller blueprint. In my player controller blueprint event graph, I use the input access turn rate and input access lookup rate events. Those events fire every frame. The access value pin provides a float representing how far the stick is pushed, usually -1 to +1, or how fast the mouse is moving. The logic then stores these values into local variables, right thumbstick axis and right thumbstick Y axis. This is the critical handoff point. Once these variables are set by the legacy input events, my event tick, in which I discussed earlier, picks them up. The event tick then multiplies these stored values by my base turn rate and delta seconds before sending them out through the camera input interface. By using this two-step process, capturing raw input in an access event and then processing it in the tick, I've created a buffer that allows me to easily scale or modify the input values, like adding the time dilation before they ever reach my camera manager. Back to the player camera blueprint. This is where I have the initialization phase of my camera system, specifically how I establish a handshake between the newly spawned camera and the existing manager. And here, the begin play, I'm performing a two critical check-in task self-registration, and taking control over the view. By calling set player camera through the player camera manager blueprint interface, the camera tells the player camera manager blueprint, I am the active camera you should be talking to. I pass self as the reference so the manager can store it in that validated camera variable in which I explained earlier. The set view target with blend node tells the player controller to stop looking through the default pawn camera and start rendering through this specific player camera blueprint. By setting the blend time to 0, I ensure the transition is instantaneous the moment the camera spawns. Going to player camera manager, I am showing you the internal logic of the set player camera function inside my player camera manager blueprint. Its sole purpose is to take the camera reference sent by the player camera and save it to the internal camera variable. This logic here works. Without this set node, the validated get in my input events would always return not valid, and my stick movements would never reach the camera. To put it bluntly, I made them this way to create a decoupled initialization. The camera finds its manager and plugs itself as soon as it exists, allowing the manager to then funnel all my controller inputs directly to it. Alright, now that I've set everything up, well, actually it goes more the lines of now that I've explained everything about this modular camera system in which I've set up, but you get the point. Anyway, bottom line, now that that's that, I'm going to test it out and see if it works. As you can see here, I'm rotating the camera with the use of the right thumbstick. Then I centered the camera. Now I'm going to do the same thing with the mouse. Click the middle mouse button. It does basically the same thing as the controller. So, in a nutshell, I've built a modular input to camera pipeline that separates where the input comes from, how the camera moves. The high level flow of my system is the legacy input manager maps my hardware to abstract names such as turn rate and lookup rate. My player controller blueprint captures these values every frame, calculates a frame rate independent scalar using delta seconds and time dilation, and sends that data out through a blueprint interface. The camera manager acts as the brain, as it receives the interface messages and performs a safety check to ensure a camera actor actually exists before trying to move it. Upon spawning, the player camera checks in with the manager and tells the controller to look through its lens, like so. Once registered, the manager funnels the process input data directly to this actor to handle the physical rotation and centering. This in turn is very effective. By setting the player camera manager class in my controller settings, I've ensured this entire custom logic spawns automatically, keeping my player's pawn code clean and focused solely on movement rather than the camera math. And that concludes this video. I hope that everything I explain here helps you out. Because with what I've experienced here, I pretty much have no doubt that it works just as fine as hell. If you enjoyed this video, please like and subscribe to my channel for future tutorials regarding to character action games. And do keep in mind that what you take and learn from me is yours to do with as you see fit. Peace out, and I will see you guys on the next video.